Okay. Right. So welcome everybody. Can you hear me? Okay. Good. So, so we are discussing the concept of localization. That's a very important tool in commutative algebra, a very flexible tool. And last time I introduced the notion of the localization of a ring with respect to some multiplicative set. And today we want to generalize this notion to modules. So instead of repeating what we have done last time, I think will just continue with, because it's largely analogous what we are doing now. So this will be also some kind of repetition. We have a new section. 3.2 is localization of modules. Okay. So we generalize what we have done. So as before, we have a commutative ring. And then we always localize with respect to a so-called multiplicative subset S. So S is a subset, is multiplicative. So multiplicative, it means it contains one and it's closed under multiplication with elements. So for instance, it can consist of the powers of some fixed element, or another important situation is the complement of a prime ideal. So these are the most important special cases. Right, and what was the goal when we introduced the localization of the ring? The goal was to construct a new ring where all these elements of S become units. So they have multiplicative inverses. So now we are a little bit more general. Now I have an M module. M is an A module. And the goal is to construct another module, which is, right, okay, maybe I should say, maybe let's go on slowly. So constructed localization. So this was this ring. Okay, and it came together with the canonical homomorphism, which we denoted this way. A is mapped to this quotient A over 1. And maybe, right, let me, okay, repeat the most important feature. This A over 1 may be 0, while A is not 0. So this map is not injective in general. And this is the case if and only if following holds, I have some S such that S times A equals 0. So A is annihilated by some element in S, right? So now I have this A module M. And actually what I want to do, I want to construct a module which is defined, which is a module over this larger ring. So over this thing, okay? And the way I do it, it's exactly the same as we did for the ring. I define equivalence relation. So what I want to have, I want to make sense of expressions like that. Sorry, M divided by S, or M, maybe I should write. So I want to make sense of expression like that. Okay, so this somehow, right. So what I do, I define an equivalence relation. On the Cartesian product M times S by saying M comma S is equivalent to M prime comma S prime if and only if, it's a definition, there is some T in S, right? And then let me write it. This is Sm prime minus S prime M equals 0. So the intuition, so I mean how, this is a definition, but maybe let me put in yellow. I mean, what we have in mind somehow is, right. So what we have in mind, we want somehow to form these objects. Okay, we want to define these quotients, and this should what I wrote should express equality. Okay, so if you multiply, if you have this, I mean, if you are purely formal, okay, you assume this makes sense, you would multiply with SS prime, then you would get that this thing, okay, sorry, this equals 0. But because we are in this more general context, we need to have this additional feature. There is a T that annihilates it, similarly as we had it here. So it turns out this is the right definition. Okay. So we denote by M over S the equivalence relation. Of the pair M comma S. Okay.
During class?
Sorry?
During the
That's right.
class?
It's sorry, it will not be. It's very hot in my room. I'm a bit sleepy, so thank you. Right, that's what I wanted to say. I think it will happen again. Okay, and by this symbol, S to the minus 1 times M, the set of equivalence classes. Okay, and then, I mean, what we do is completely standard, right? We want to have a module, okay? We turn this into a module over this bigger ring as this one. This module into module. Or if I say bigger, it's not correct. It can also be smaller, but this localized ring. And what do I do? Okay, this is the definition. I define addition. Well, how would I do it? I mean, I want to maintain my usual rules of operation. So the only way to define it would be this. Okay, and of course, the crux is one has to verify it's well defined, which is straightforward. Or the scalar multiplication. Now, the scalar is an element in the localization of the ring A. It has this shape multiplied with an element in my localized module, which has this shape. And what it should be is this. Okay, this is the definition. And then one has to work a little bit. One has to check that it is well defined, but I will not check it for you because it's very boring and trivial. And axioms, it's all trivial to check. And it's the same, basically the same as we did for the ring. Okay. So after having done this, we have a module. And this module, as always, comes with a homomorphism. So I map M to this new module. And what I do, I map the element M to M over 1. Okay. In many cases, it will be injective. Then M is a submodule, but it's not always the case, which causes some problems. So this map is A-linear. Okay, now I have to be precise. M is an A module, but this is a priori not an A module. It's a module over S to the minus 1A, but via scalar restriction, I can view this as an A module. I should write it if this is considered as A module via, right. Okay. Okay, I can say, how do I write it? Maybe I should write explicitly what is the yeah. Mm. Okay, maybe I have to, sorry. Continue. Okay, okay, via, I mean, I have this homomorphism here. This is also the canonical one. Okay, and then I can do scalar restriction. So scalar restriction. So, I mean, what would it be? I mean, okay, let's write explicitly what it would be. Like you have an element here of this module, you multiply with A. I mean, the only reasonable way to define it is this. So it's a lot of talking and writing about something very trivial. Okay, there's something that I need to shut down, sorry. There's some app which is annoying. Good. Okay, so, and then it's important. Okay, there is some program starting that I have to kill, updates and so on. Sorry. So it's gone. So when is this injective? So m over 1 equals 0 if and only if, and this is by definition, there is a t in S such that Tm equals 0. This is the definition, okay? So, right. So this is very abstract. We will see examples. So this localization has beautiful properties, And right, some notation, very common in commutative algebra. If we localize with respect to a prime ideal, we name it, okay, right, M index P instead of S to the minus 1 M when S is the complement of a prime ideal. Okay, so this is the symbol here to remember. We localize with respect to the prime ideal. Okay. Also write M index F. Okay, for okay. If I localize with respect to the powers of an element F. Okay, write it this way. Okay, so we had this notation before, I think, when M equals A. So we should just remember it, these notations. Okay, so it's not enough to assign to these A modules, new modules, we want to have a functor. Okay, we also need to have such a association for the maps. So if I have an A linear map, so let's do this now. Suppose U from M to N is A linear. So needless to say, M and N are A modules. I have an A linear map. Now I want to assign to it a corresponding linear map of the localizations. And how can we do it? Okay, so how do we do it? I need to have such a map. Okay, and okay, the obvious way of trying is this, M over S. Okay, you see there is a difference to the tensor product. Here it's easier because every element here has this form, right? So I have an element and then I map it to what? Okay, I map the M, I have U of M divided by S. Okay, and then so it has a name, S to the minus 1 times U. Okay, well defined. This is again a trivial checking and linear with respect to this big, to the other ring. Okay. I don't know, maybe I don't write this. You check yourself. It's very trivial. This is a trivial verification. Okay. And then what one checks are these functorial properties. It's also clear. So if I compose, let's say I can compose two A-linear maps, I localize, then I could first localize and then compose. Okay, and if I localize the identity map, I get the identity map on the other space. So this means I have a covariant functor, means covariant functor. A functor. Okay, two categories. One is the categories of A modules, and the other is the category of S to the minus 1 A modules. Okay. This is exactly the meaning of that. You map the objects, you map the maps, and you have this functorial property here that I wrote. Okay. Good. Other questions on that? So. No questions. So what is good about this functor, it preserves exact sequences. So in a way, it's better than the tensor product, because the tensor product, you know, it was only right exact, but not left exact. But the scale, but this localization is perfect. So let's write this. That's the next proposition. Be free. Okay, the functor. Okay, I write the functor S to the minus 1. Okay, maybe is exact. Okay, and this means concretely, it means the following. If I have an exact sequence, okay, I don't have to write a long sequence, just a very short one. I have three members. I have go from M prime to M, from M to M2 prime. I call these A linear maps F and G. If this is exact, then the corresponding sequence after localization is also exact. So everywhere I have to put the S minus 1. And this is S to the minus 1F, S to the minus 1G. And the point is, this is exact as well. Okay. So clearly, M prime, 2 prime, these are, okay, I don't write all the assumption, I think. Here I have A modules and A linear maps, and then I get this.
But don't you still have to write the zeros?
On the left or something, or yeah. No? You mean I should, okay, do you mean I should have something like that, or?
Yes.
No.
Okay.
No, I don't think so. No, I mean, this is maybe the most, this just means if you have this, then you can take any sequence, okay, exact sequence, and you look at it very locally and you get it. Okay, so maybe this is the strongest statement one can have. Okay, proof. Okay, none of these proofs, I mean, you understand, none of these proofs are difficult. Somehow, when I do this lecture, there are moments when I envy people in combinatorics because sometimes they, you know, they have tricky proofs. I mean, there are here, it's all in the concepts. Okay, but a lot of mathematics is like that. It's all in the right definitions. And then when you have the right definitions, like the proof takes go automatic in a way. Okay, so Good. So let's start. When I first do F and then G, I compose, then I get 0. Okay, because I mean the image of F is equals the kernel, so the image of F clearly is contained in the kernel of G. So I have this. Okay, then I apply my functorial property. So I apply my functor. Now this is s to the minus 1 of the composition, because here I used it's a functor, and this is 0. This is the localization of 0. This is a 0 map. So this means that the image of s to the minus 1f is contained in the kernel of s to the minus 1g. So this was like the first part of the proof. Okay, and what I need to prove is that here this is equality. I need to prove equality. So this was the easy inclusion. So now let's do the converse. Conversely, so I take an element that is in the kernel m over f, that this be in the kernel. Okay, so this, what does it mean? Okay, I map it. When I map it, I get g of m divided by s, because that's the definition. That's the definition of this map, and this equals 0. So this is 0. Let's always say where this is 0 in this module. Okay, 0 here. Being 0 means, by definition, there is some t in S, so that after multiplying with t, how do I write it? T, maybe I write, okay, I write from the right to the left. T gm equals 0. But tgm is this. So I have this. Okay. Now, okay, now I am in this world. Now I'm here. I have an element Tm here, which is mapped to 0. Because I know that this is exact. This Tm here is f of something. It's in the image of f. So there is, therefore, because now I use the exactness, there is some m prime with the property Tm is f of m prime. Okay. Right, and then we just have to see what this means. We are essentially through. So I claim m over s is mapped to what I want. Okay, m over s is the same as tm over ts. In German, it's called erweitern. Okay, fraction. Tm is f of m prime divided by ts. Okay, and but this was our definition of the map s to the minus 1f. This is the image of this of m prime divided by ts. Okay, so this is in the image. And I'm done. Okay, I started with the element in the kernel here, and I show this in the image. So it's just calculus of fractions. Okay. As I said, the only tricky thing here, so the only reason why this is not completely trivial, everything is this, right, where is it? The zero-ness, okay? So when you go to the localization, things may collapse. So it's, nevertheless, everything works if it's properly defined. Okay, so in particular, this is nice. So if you have an injective map, it will stay injective. If you have a surjective map, it will stay surjective. So in particular, okay, if I have, okay, if that's, let's say if this is an inclusion, is inclusion. So let's say M prime is a submodule of M, then this map is injective. is injective. Okay. So we may, okay. So we may assume it's an inclusion. I mean, just okay, we may view it. Wait. May view this as an inclusion, maybe you. And actually we do it if it's okay, if it's convenient, I view this as submodule of this. So in a way, submodules become submodules. Okay, right. So this was one property, exactness is preserved. Now, next proposition says that the localization behaves nicely with respect to other operations on submodules, namely you form sum of submodules or intersections, or okay, you form quotients. That's all very nice. So that's why this localization gives really, in a way, a calculus. Okay, you can formally operate with these objects in a really nice way without thinking too much. If you know the rules, you can just operate without thinking. Okay, so taking localizations. With respect to S, commutes with. So what do I have? Sums, direct, okay. What do I call it? Sums. Okay, intersections. Okay, I think I want to have finite sums, actually, finite sums. Okay, I could also say direct sums. Okay. Also through finite intersections and quotients. So let's write it down explicitly. Let's only write it for sums of two or intersections of two. Okay, for submodules, just to save notation, N and P of M, okay, of a module M. We get the following. Okay. So I can form N plus P. So it's a sum. It's a submodule. I localize it. Okay, I view this as a submodule of the localized module. The other hand, I can do this and this. Okay, view it as submodules. I take the sum, and the claim is this is equal. Or intersection, same thing. You intersect, you localize. This is set theoretically the same as this. Okay, and the third property is, okay, we take the quotient of A modules, then we localize it, and there is a canonical isomorphism with this. You have this. We know this has as a submodule this. This is what I just explained. Okay, this is basically this. Yeah, submodule is just different notation. So I can form the quotient. This is a canonical isomorphism, or yeah, canonical isomorphism. And when I show the proof, it will become clear why it is canonical. Okay.
A question about that.
Yes.
You just told us before that it's sums or direct sums, but it's actually not the same. So it's true for both sums and direct sums. I mean, it's the same.
But if it's true, okay, if it's true for a sum of two, then it will also be true of a direct sum. I mean.
So you mean direct sum intersection is 0, and then
yes,
we do it
yes,
as a sum.
this is a special case.
Okay.
Okay, right. Good, I mean, I don't think there is much to prove here. I mean, most of it is clear. I would say A is clear. I mean, you just write down how do the elements of these objects look like? And then that's what it is. No, I mean, there's nothing. For maybe two, a little reasoning. So on the one hand, one inclusion I think is obvious. N intersected P, if I localize, just set theoretically, it's contained here. And it's also contained here. So it's contained in the intersection. And a little argument is required to show that we have equality. And the point is, there is a very little argument. The point is now, if I have an element here and here, it may come with different denominators. So we have to clear denominators. In German, we say gleichnamig machen, okay? But of course, we can do that. And this is the proof, but maybe let me write it. So conversely, so I have an element, let's call it y over s, which is also c over t. So this is in the intersection. Okay, every element in the intersection looks like that, where y is in n, z is in p, and s and t are in s. Okay, so, okay, right. Then, as I said, okay, let's remove these denominators, take away these quotients. But we know then there is say a u in S such that, okay, I write what this equality means. And this means there is a u in S such that, okay, ty minus sc multiplied with u equals 0. So it's again this. If this would be a normal fraction, then this equality would be equivalent to this being 0. But because we are in this localized setting, we can only say this after multiplied with some element in S becomes 0. So I have these things here. Right, but it doesn't hurt. It doesn't hurt. It doesn't hurt. Just have to be careful. So UTY means USC. Let's call it W. Now we see this is, on the one hand, it's in N because it's a multiple of Y. On the other hand, it's in P because it's a multiple of Z. So this is here. Okay, and now let's divide again. Okay, what I can do. UTY, I divide by UTS. Then this is the same as Y over S. Okay, I clear T and U. On the other hand, this is W divided by UTS, and this is clearly an element in the localization of N intersected P. Okay, so I have shown that this element, what have I shown? So I've shown that this element here, Y over S, in fact lies here. Okay, good. And how about the last thing about the factors? Right, so I write this, okay, I have this short exact sequence. N is a submodule of M. So I can write this exact sequence. This is exact. Okay, right, I assume that. And then I apply my functor. And I know the functor take s to the -1 is exact. So I get this exact sequence. Okay, but does it mean? It means or implies it implies that this is isomorphic to this quotient. And I said it's canonical. Well, we know the isomorphism. The isomorphism comes from this sequence. And all the maps here, they are the natural one. I mean, what should it be? Okay. So everything fits together nicely. No surprises. Okay, it's machinery. Okay. Questions on that or? Right. Still, I don't think it's so trivial. I mean, if you've never done this before, then I think you easily get confused. So really one has to, okay, one requires a little bit of training with these methods. Okay, so what is the next topic? So I introduced localization, but before I introduced the tensor product. So the question is, what is the relation of the localization with the tensor product? Okay, how can I relate them? And it turns out they relate really nicely. And the first, okay, there are several insights here. Maybe the first insight is that the localization of a module can be understood if I only know what is the localization of a ring and I have the notion of the tensor product. Okay, so I could have saved time in a way. So this is the next proposition. I can express localization of modules via tensor product. So let M be a module and S multiplicative set, multiplicative closed, multiplicative closed, I think I write this way. So two statements. One, the scalar extension. I had the notion of the scalar extension, if you remember, the scalar extension of M. M is an A module. With respect to the ring morphism, okay, so here, this is the one coming from the localization of the ring. So I can extend scalars and turn M into a module over this ring. And the statement is, what I get is this. I get the localization of the module. So more specifically, we have the following isomorphism. Okay, have isomorphism. Right, okay, I want to write the isomorphism. I write here on the left, what does it mean to make a scalar extension? So I have my module M. Okay, I want to make scalar extension. Then I take this tensor product with this ring. Okay, this is the tensor product of A modules, but then by our general considerations, here is a ring as well. I can view it as a module over this ring. And this is exactly the scalar extension. Okay, on the other hand, I have my localization of the module. Now I have to write a map. And what could that map be? Okay, so elements here generates in the, okay, elements in the localization look like that. I take an element is M, I take the tensor product. So every element in the tensor product is a sum of such things. And the map will send this to AM over S. Okay, so this is well defined in an isomorphism. Okay. So you see, instead of writing this way, I could have written it this way. And structurally, that's what it is. Okay, the localization of the module is a scalar extension of the module with respect to the localization of the ring. Okay, and then another statement, the next statement is, this is also true with regard to the maps. Okay, I can also scalar extend maps, A-linear maps, but I also have localization of A-linear maps, and this is all the same. So let me write, that's also very important. So let U from M to N be a linear. So I write the commutative diagram, which explains hopefully everything. So on top, I write the localization map. So this is s to the minus 1 u. Okay. Then here vertically, here is the isomorphism of part 1. Okay, and I get a similar one, an analogous one for n. Okay. And now here, what do I have to put here? So it will be the commutative diagram. Well, what would it be? The scalar extension of u. And this was defined by taking the tensor product of the identity on this ring tensor u. And the point is, this is commutative. This is the diagram is commutative. Okay. So sometimes I like to write it this way. I don't have to put a lot of text. Right. Okay, but I think you see the usefulness of this insight in a way. And I think you could prove it. I mean, if you understand the definition, right? But let me show it. Let me go through the proof, okay? So what else? Okay, the first statement. Let's do the first statement. Okay, so how will the proof go? I have to set up this map, and then I have to show it's an isomorphism. Okay, setting up the map is pretty obvious. Okay. At the risk that you will say it's always the same what I'm telling you, I would say the map. Okay, I start with the bilinear map. Okay, this one. The map. Okay, it goes sends a over s comma m to this am over s. So this map is a bilinear. That's how we start. Okay, this is a bilinear map, and here therefore defines by universal property of tensor product defines a linear map. And this is the map that I need. This is this one. Okay, and if we call it f, then f of as tensor m will be am over s. Right. Here I don't need parentheses, sorry. Okay, here I need. Okay, so I have this map. It's there. Now let's see why it is an isomorphism. It's surjective. I think this is clear because here, you see, in particular, here we have the elements m over s. Take a equals 1. And every element here is of the form m over s. So it's clear that it is surjective. Clear, f surjective. So this is clear. So, and the claim is f is injective. So let's do the check that f is injective. Okay, so now a little difficulty. Okay, well, it's not a real difficulty. The elements here, they are not just tensor products, they are sums of tensor products. So any element of this guy here is of the form, it's a sum, a finite sum, ai over si tensor mi. Okay. Right. So it looks like that. Okay, where, of course, AI in A, SI in S, MI in M. Okay, so now I assume it is mapped to 0. Okay, so I map it. So if I map it, I get this AI, SI. Let me see. No, sorry. At first, I don't map it. At first, I want to rewrite it. Sorry, it's hot here in my room. Okay, I write it, and the point is, I put it on the same denominator. Right, actually, let me move down this. So it's just calculus of fraction. So I define S as the product of the SI. Of course, that's in capital S. And then the cofactor is TI is the product of the SJ, where J is not I. So SI times TI is small s. And then, okay, just gleichnamig, in German would say gleichnamig machen. That's what we do here, nothing else. Okay, so then how do I write it? So I write here EI TI divided by SI TI tensor MI. Okay, and but then I see, okay, this is 1 over S. SITI is S, and the AITI I move to the other side. This I can do because of bilinearity. Okay, then I see this is, I can pull out 1 over S. It's 1 over S tensor this thing. Okay, so this is a 1 over S tensor, an element of the module M. So therefore, any element of my tensor product is of this form. Any element of this has this form, So you see, this was kind of an auxiliary argument. Some S in S, M in M. Okay, I could have said this outside of the proof. Every element of this tensor product has this form. Okay, this is maybe something to remember. Okay, now assume I want to show injectivity of F. Now suppose F maps this element to 0. Okay. Now we have to see what this means. So then, if you haven't forgotten, I mean, what does the map do? Here is the map is defined. Okay, so it means M, okay, where is it? M over S equals 0. And this means there is some T in S such that T times M equals 0. And then I just go on, it's the usual blah, blah, blah. I want to show, right? I want to show this is 0. Okay. Right. So let's see, why is that 0? 1 over S tensor M. So the clue is multiply here with T and then move T to the other side. STTS doesn't matter. But TM is 0. So get 0. So F is injective. Okay. You see, it's this. I had this trick before. Okay. We want to show something is 0, move it to the other side. Okay. Where it becomes annihilator. Right. And how about the other? Okay, this was part 1. Part 2, so this is the commutativity of the diagram. I mean, there's not so much. I mean, we just write down here, I'm here now. We just write down what the maps do and check it's the same. So let me verify. Let me write it down. On generators. So down here, I have A over S tensor M. Up here, I have AM over S. So this is the one map. Then this is the localization map. Goes to, what is it? UAM over S. That's the way how I defined it. But this is the same as AUM over S. And down here, I go to that's how this map is defined. And then you see if I go up, I get the same. So it's commutative. And I'm done. Okay. Questions on that? It just works. Just works. Not much to, yeah, just works. Right. Yeah. By the way, it's in now. It's so it will not be boring. I'm writing a paper with a couple of people, and there are also some younger, less experienced people. And no, I'm rewriting this paper, and in a way, what I'm doing, I'm not even at the moment. I don't not even add mathematical content. I just rewrite it in a way to make the structure clear. Okay, because once there is some structure there, but if you write it poorly, you don't see clearly the structure. Okay, there are lots of the same type of proof appearing several times, repetitions, calculations. If you identify what is the right structure, it becomes shorter and crystal clear. And in a way, I think that's the task of algebra. I think that's what we are doing here. Okay, in a way, analyzing the structure, right? But in the end, the arguments are not difficult. You just need to make the right definitions. Okay, this is kind of an excuse for this kind of thing. It's really useful to have these. Okay, then, okay, what is a corollary? Okay, this is 3.6. Okay, we didn't talk a lot about flatness. There is not much time, but you remember the definition of a module being flat means that if you tensor with that module, exact sequence stay exact. It's the preservation of exactness. Now, what we have shown here, actually, that was the other thing. It was the previous, it was that. No, it's sorry, confusing. I don't find it. Oh, okay, here. The functor localize here is exact. Okay. So we prove that. Exact sequence go to exact sequence. But then we realized that actually this S minus 1 to the F, this is the previous result, is this, is tensoring. Okay. So, I mean, what we see now, if we combine these two observations, we can say this localization is a flat A module. Okay. And the proof is just combine proposition 3.3 and proposition 3.5. Yeah, you have a short exact sequence of A modules. Then you tensor. Okay, you do the scalar extension. You get a sequence of modules over the ring S minus 1 to the A. But this, what you get, is the localization. That's the previous proposition. And we realized, we said localization is an exact functor. So this is just another way of saying this phenomenon. Okay. Okay, then questions on that? No.
Can you maybe repeat the argument? I didn't really
Right.
understand.
Okay. Maybe I do it in yellow. Okay, flat. What does it mean? I eh, Okay, let's assume these are A modules and it's exact. Short exact sequence A modules. Now, what I have to do, I tensor. Okay, I form this sequence. It's a lot of writing. I get this sequence. Okay, this is a sequence of A modules. The question is it exact? Okay, I have to show it's exact, right? Then this is the meaning of flat. Flat means that whenever you have such a short exact sequence, you form this, it will be exact. And why is it exact? Because this, I mean, this is canonically is the same as this. Okay. And even the map, I mean, so here you see the maps here. These maps are, maybe I can write, okay, maybe I should write it. Maybe if this is called F, I don't know. Then this map is identity tensor F. Of course, identity on S to the minus 1A. And this map is S to the minus 1F. And we know this is a commutative diagram, right? So if I want to show that this is exact, I just show that this is exact. But this is exact since this S to the minus 1 is exact functor. Is it clear now? Okay, good. Right. What else? Okay. Good. So, right. So I have I have two A modules. I can tensor them, get an A module, and then I can localize. Or I can first localize them, then I get modules over S to the minus 1A, and then tensor them. Statement is, what you get is the same, canonical isomorphy. That's another nice property, very useful. Maybe I put it on the next board proposition. So, okay, the statement is this, localization commutes with tensor products. Tensor product with the operation of taking tensor products. So that's this. So M and N, let M be A modules. And S is like the multiplicative set, multiplicative closed, I think I write usually. So then, okay. So on the one hand, I do this and this. Localization of modules. These are modules over the localized ring, so I can form the tensor product. This is a module over S to the minus 1A. On the other hand, I can first take the tensor product. So I have an A module, and then I do localize it. Let's put parentheses. Sorry, no. I have to write it this way. Okay, and there is the statement is it's isomorphic, and I can write the map. The map is just a map that it. What else can it be? You have here a generator M over S tensor N over T, and you can map it to M tensor N, and then over ST. This is isomorphism of S to the minus 1A modules. Okay. Right. So in a way, I don't know. It's like if you think purely formal, okay, you just manipulate symbols without thinking about their meaning, it's like some associativity. I mean, or the order in which you do things doesn't matter. Okay. So let's write a special case of this, which is very important. So in particular, if we localize with respect to a prime ideal, in particular, if P is prime ideal of A. So I write it, so you have seen this. Then if I localize with respect to a prime ideal, the localization is denoted NP. And here I have NP. And then I take the tensor product with respect to the localized string is AP. And I have an isomorphism. Or I could just take the tensor product over A and then localize. So maybe let's put this to yellow frame. Okay. Okay, I need to prove it. Now I realize. Okay, in the proof, that there is one step that relies on an argument, the general argument that I skipped in order to save time. So let's see what I can do. It's not a difficult thing, but there's a little gap, the argument. So let me do the proof. So by the proposition 3.5, so what is the idea of the proof? The idea of the proof, if there is any, you express everything in terms of tensor products. So in the statement of this proposition, I still have the operation of tensor product, we have the operation of localization. But I realized before, localization is also tensor product. So I write everything as tensor product, and then I use at some moment some associativity of tensor products. Okay, which is a little bit tricky because rings change. So this is the, so I write, okay, this and this. So I rewrite it, always trusting that these isomorphisms are, you know, canonical. So then, okay, maybe I write here, I needed some space. So okay, I write the left-hand side of what I want to do. So this is what I want. Now I plug in, I replace these two things by these two things, but I put parentheses. Okay. Tensor, but okay. Okay. Right now, okay. So how the difficulty is somehow now we have these different rings here. Okay, let me write. Okay, let me write this general principle that I want to apply, but without proving it. But at least you will see the logic. Maybe I should have said this before. Okay. You know, I do the following. I write it. Okay, let me first do this as a little intermission. Sorry, I should have. Let me move this down. I need some space. Okay, I continue because there is something that okay, little intermission. Intermission. So there is some result, and this is actually exercise 215 in a Tia McDonald's. Let me at least write the statement, and I want to apply this. Okay, so I have rings, A and B are rings. Commutative rings, M is an A module. And P is a B module. But, and N, this is a module over A and over B. Okay, this is possible. It can be a module over A and over B. Then I have two actions. And I want these two actions to commute. So there is a name for that. This is called the B module. N is an ABB module. So maybe yellow, B module. So means, okay, N is A module. And N is a B module. And the two operations are compatible in the sense that, okay, let me write for all A in A, B in B, X in N. Okay. So, okay, now it's convenient. Okay, let's write the multiplication with A on the left and the multiplication with B on the right. It's not important, but it kind of makes the writing nicer, okay? So what I have here. So I write this written as a right multiplication. Okay, there is nothing deep about that. It's just convenient. Okay, I could also write everything on the left and okay, assume that it's commutes, but this is very common to do it. So you see, I just write the here multiplication on the left with B on the right, and this expresses its commutes. That's all. So this is a B module. Okay, so then if whenever I have such a situation, then okay, I realize this can be very confusing. Okay, so when I write this, for a moment, I forget that N is a B module. It's just an A module. Then I take this tensor product. It's an A module, right? But it's not only an A module, it's also a B module, okay? Is A module, but also B module. Why is it a B module? Yeah, because okay, of this B module thing, maybe write B module. The scalar multiplication with elements of B just takes place on this side. Okay. Same thing, right?
Sorry, you were just gone for a couple of seconds.
You could not see.
Yes,
I was frozen.
yes, maybe from the point on why it's also a B module.
Okay. Where from exactly? Where should I?
Why is it also a B module? That was the.
I didn't say that. I explained.
Okay.
I explained. This was the definition. This was the definition of a B module. Okay. So far, these were all assumptions, including the definition of the concept of B module. Now comes, I want to write the statement, but I explain. Okay, I go slowly. First, I say I form this A module, a tensor product, and I notice this is not only an A module, it's also a B module, where all of the scalar multiplication with B takes place here. And I can change the roles. I can also write N tensor P. This is, now here is the tensor product of a B module. It's a B module, but also A module. And also here, the A scalar multiplication, just because of that. And having said this, after all this explanation, I can write the statement, okay? We have canonical isomorphism. So, I mean, it's easy to remember in a way. So I form this. And then I form the tensor product with P. But this is, okay, a tensor product of P modules. On the other hand, I can also do this. Tensor product of P module. And then remember, it's also an A module. Form tensor product as A modules. And statements is isomorphic. And the map, I mean, what will it be? Okay, maybe I'm pedantic and put here an A and here a B. This is mapped to X tensor. This is the map. Okay, so okay, I don't want to go into the proof. It's I don't know, maybe Marco wants to do it or not. Oh, sorry, I killed this. Sorry. Just having, right. So, but I just use it. In a way, it's, you see, on a few purely formal viewpoint, it's a kind of associativity. Okay, so let's use this, okay? Let's use this. So we return to the proof of our proposition. So here, what was it? Right, localization commutes with tensor product. So I'm back here. Okay. So what do I do? Here, I have this. I plugged in these formulas for the tensor product of modules. So now let's apply this associativity and let's apply it twice. So I go really slowly so you can, you know, verify every step. Okay. Okay, apply. I think I will apply it twice. Okay, apply. Previous associativity. Okay, for the sake of clarity, let P be any B module. Okay, I think it will be clearer if I do it in this generality. Then, okay. Now maybe I rewrite the statement. So I rewrite it. Okay. Should be. Okay. So what one has to, let's check. Can I compare? Right, we can compare. Right, we are in the situation, but instead of N, I write B. So B is my B module. Well, that's okay, right? So what is B? Right. No, sorry. I'm confusing. I'm really, excuse me. My apologies. Sorry. Today I'm sleepy. I removed this. Really sorry, because I wanted to go and prove this exercise. No, I don't want to do this. Too hot. Sorry. I said, hopefully it's the last time. 10 more minutes, no more error. So now, okay, now I hope now I can do it. So now I want to apply this associativity. So I view this thing. as a B module. On the one hand, I have A, and on the other hand, I have this B module. And apply above associativity. Okay, so this is the B module. There's nothing fancy about it. Okay, so what do I have? M tensor. So I hope I'm not making it too complicated. Aha, now what I do, okay, now I remember what I wanted to do. I go in 2 steps. Let's call this guy P. Okay, so here is the A module. Okay, clearly, I mean, B is this, okay? This is the B, this is the A module, this is the B module, and this is the B module. Okay, good. Now I use the principle which I didn't prove. Okay, reset the parentheses. Okay, now you see, but now what is nice, right? Here, this is just P. Okay, because, yeah, you see, like P tensor B is P, because this, okay, the tensoring with the ring itself is like the 1. You see? So this is just this. Okay, so I have this. Now I continue. Okay, maybe I rewrite. So this is, now I plug in what P means. Okay, good. But now these are just A modules. This is also associativity, but it is a little bit less, easier. Like this, associativity. And okay, I can the order. Oh no, sorry. No, this is too bad. Not only, I also use commutativity. Oh my God. Okay, the order of things doesn't matter. So, okay, commutativity, associativity. And then I realize this is by the proposition 3.5 again, nothing. This is just a localization. Okay. So and this was the proof in a way. Sorry for that. Okay. But there's right. Localization you express as tensor product, and then it's associative. And there is a little bit of a sophisticated argument because the rings change. But otherwise, that's it. Questions on that?
Just for bookkeeping, maybe you could specify that this is the proof of proposition 3.7. Because you had the associativity thing in between.
Good. Proposition proof, correct. Thank you. So this makes the nodes easier to trace. Thank you. Go back to step 4. Where am I? Okay, next property. Right. Okay, good. Okay, I think I'm through with this section. So, okay, there is another section. It's also in the Attia Macdonald. It's called local properties. So this is in a way one of the main applications of localization. The name localization means look local. Don't look at the whole thing, just look at the small part of it. Right. And there is also this geometric intuition about it that I try to explain a little bit. And yes, there are some properties that are local. Let's define what this means. So a property of modules is called local. Okay, if. Okay, I write it generally. Okay, M has this property. Maybe let's call M has property. Let's call it P, property P, if and only if all localization at prime ideals have this property. Okay, for all prime ideals, primes, P of, okay, A, the localization has this property. So if there is something unclear about the definition, as soon we look at the examples, you will understand what I mean. Okay, so next result. So the property that I'm looking at is a very simple property, is the property being zero. Property of a module, is the module zero or not? I want to prove some A module is zero. Now the statement is I can do this by just showing that all the localizations at prime ideals are zero. Actually, it's enough to look at maximal ideals. So let M be an A module. My problem today is that the others of my family have drinking up all the coffee. So I couldn't get a coffee quickly. There was not enough time to prepare one. That's I made this why I make these mistakes. Blame always other people for your errors. So one is module is zero. Two is localization is zero. Okay, one problem is also yesterday, the game, the soccer game, you know, Switzerland. So it was very late. Do you know that? You know this? You don't know? Switzerland kicked out the world champion, France. That's amazing. Okay, it's a very special day. So the localization is zero for all prime ideal P's. P of A and 3. Same property for maximal ideals. Maximal ideals. Ah. Of A. Okay. Okay. So let me do this. It's okay. I need some more board. One more board, please. Okay, good. Proof. Okay, if every time I start 5 minutes late, and so then in the end, I don't arrive anywhere. So I have to do this. Okay, there is a chain of implications. 1 goes to 2. This is trivial. If you localize 0, you get 0. And for 2 to 3 is also clear. So this is clear. So we only need to show 3 to 1. And it's easiest to do contraposition, show contraposition. So I assume I have a module M that is non-zero. Suppose M is a non-zero module. And then I have to find a maximal ideal such that the localization with respect to that ideal, maximal ideal is non-zero. So how do we find maximal ideals? We only have one technique in this generality, and this is via the Zorn's lemma. Okay, we have a proper ideal, we extend to a maximal ideal. Always that trick. So what kind of ideal will I take? Okay, which I will extend to a maximal ideals? It will be an annihilator. Okay, so let's say X is non-zero. Non-zero element. Okay, then I look at the annihilator of X. Okay, this is an ideal and it's properly contained because X is non-zero. Okay, otherwise there would be one. It cannot be. Okay, now there is a maximal ideal via Zorn's lemma. Let M be a maximal ideal such that, okay, well, which contains, okay, the annihilator. Okay, good. Good, and this is my maximal idea. I just have to check, okay, I claim, okay, if I interpret, okay, the image of X in the localization, I write X over 1, and I claim this is not 0 in the localization. Okay, now let's check. Okay, why is it non-zero? Okay, maybe indirect. Otherwise, X over 1 equals 0 in NM. So this means there is some element. I used to call it S. Maybe I should, okay, right. Why not call it S? There is an S in A, but not in M, such that Sx equals 0. Okay, so, okay, so my S is in the annihilator. But this cannot be because S is not in M. Okay, the annihilator is contained in M, and I say S is not in M. This is not possible. Okay, so I'm done. Right? Question on that? No question. Okay, can I, right, stop now or go for another 3-4 minutes to catch up a little bit of time? You tell me. I'm afraid I'm a little bit behind schedule. Okay.
From my side, would uh, I would say that you can go further. I don't know what others mean.
Right.
I don't mind either.
Sorry.
I wouldn't mind going on a further.
Okay, then let me do the next thing. Thank you. I need no space. Okay. Thank you. Right. This is the next. I hope I can fit it on this board. So it's about maps. So I have an A-linear map, phi. This is A-linear. Okay. Again, I have 3 conditions that are equivalent. Equivalent are, first, the map is injective. Okay, I want to test that the A-linear map is injective. And then it's enough to test it in the localizations. So here I localize this thing with respect to a prime ideal, which I denote with phi p. I'm not even sure that I defined this, but this is the localization. The localization should be injective for all primes P of A. And the third statement is the analogous thing for the maximal ideals. For all maximal ideals. M of A. Okay, and the same, okay, statement holds for surjective. Same statement holds for surjective. So injective, surjective, these are local properties. Isomorphic also will be local properties. So proof. So sorry, let me put here something black, otherwise it doesn't, the white is a bit disturbing, the color. So okay, then I have all black. So how do I do from 1 to 2? Okay, that's easy. I use the exactness of the localization functor. So if I have an injective map, I can write it as a diagram. Okay, yeah, this is exact. This expresses phi is injective. And then I apply my proposition. It's a proposition 3-3. Okay, I localize, and what I get must be exact. Okay, so this means phi p is injective. Okay. Okay, good. Then from 2 to 3, this is clear. So the only thing remains to prove 3 to 1. Okay, this is the interesting part, but it's not too interesting. It relies also on, yeah. Okay, the idea is now I reduce to this statement. Before I showed something being 0 is a local property. Now I want to reduce to that. So, okay. So I assume 3 and I want to show phi is injective. So let's give a name to the kernel. Let's call it M prime. M prime is the kernel of phi. I want to prove M prime equals 0. Okay. Okay, then I just look. Okay, let's first express this by a sequence. So sequence. Okay, I have the exact sequence. 0 M prime M N. So this is exact. Here is phi. The other is the inclusion. This is exact. Okay, then proposition 3-3. Okay, I take scalar extension with respect to a maximal ideal M and I get an exact sequence. So everywhere I put the index M and M, and here is phi M, and this is exact. Okay, good. Now we just have to decode what this means for all M, okay? Okay, for all maximal ideals M. I can do this. Okay, now, if I look at this diagram, I see this guy here. Right, what do I do? Okay, maybe I show it. This map, sorry, this map has a kernel here, but the kernel is the image of this, but this is an inclusion. So the kernel of phi M is this. This I can see as the kernel. Okay. Okay, now comes the assumption. The assumption is that the phi M is injective. So this is 0, this is the assumption. Okay, the assumption is for all M. Okay, for all M. Okay, so I have this for all M. Right, now I use that being 0 is a local property. This is proposition 3-8, and I conclude M prime equals 0. And this means my phi is injective. Okay. And in order to do the same thing for surjective, you see this is a completely formal thing. Just reverse all errors. Okay, surjective. You check it yourself. Reverse all errors. Just formally, all the errors reversed, same argument. Okay. Okay, I think that's it. Let's stop the recording.